So people can do things like cause the CPU to malfunction, force the program to do something else by rewriting the code, or you can take away data that is stored in the memory, or cause the analog part to malfunction. For example, if it's a pulse width modulation, see, that is used to control the speed of the motor. But if you are willing to do something wrong to that analog chip, it may cause the motor to spin very fast, right? So is it possible for this hardware to be self-aware and avoid running all kinds of software, forwarding all kinds of packets, respecting all kinds of requests, right? How does one architect such systems? Should it be AI agent based? Okay. So should we use what are called as agentic systems? Nowadays you may have heard this term, right? Agentic systems. So that's another important consideration. People can use fault injection attacks. Okay. So using voltage manipulation, temperature manipulation, clock manipulation, they can inject faults. Okay, that person has to have an intimate knowledge of the hardware, and likely sometimes these things happen because of disgruntled employees who may leave the company. Okay, they are very much aware of the hardware. So faults are injected to cause errors. See, even a 1 bit change can change the instruction, right? Because the machine code, see, that 1 bit change can change the entire meaning of the instruction. It can cause the conditional execution to be skipped altogether. If some condition, then do this, else do something else. Okay. Now, if I am willing to change this bit from 1 to 0, then something important may be missed, causing a problem. Okay. And there are also some sophisticated ones like atomic force microscopy, which can read data stored as local charges in the memory chips, and they don't need to even remove the lid of the chip, etc., right? So they can steal data very easily. So there are many smart sensors today in our equipment, right? For example, transceivers, and the transceivers may be used in gateways, and the gateways talk to the server. So you can inject faults to cause denial of service, prevent transmission of data, or communicate wrong data, all kinds of things. Say, steal sensitive information, prevent transmission, gain control of actuators. So at different levels, different kinds of security threats exist. And people can use your JTAG or the boundary scan, which is intended for debugging with they can use that to steal data. Okay. That's called as a side channel attack. Okay. So the physical fuse can, so here is a way to prevent such things, right? So they will place a fuse in this place, right? And when you are done with the testing, you can blow that fuse so that nobody can use that test mode signal anymore. Or you can use a password protection to use JTAG. Similarly, there are other techniques that are used in software IP protection. I will not go through this because it's not relevant to this class. So today, a lot of security is added to our chips. Okay, they use encryption, decryption, right? These are all encryption, decryption algorithms, password checks, uh, locking peripherals, right, and so on and so on. So verifying security itself is a big issue, right? I will not go through this. This also I'll skip because it's not relevant to us, right? This is something that we may want to understand. This is the, I think I mentioned this earlier. Okay, I mentioned to you that there is a cell, and we normally tend to look at only the faults at the periphery. Stuck at 0, stuck at 1, stuck at 0, stuck at 1, stuck at 0, stuck at 1. But inside there may be a lot of other faults, right? We have mentioned this before. So this XOR gate may actually have been built like this. So if you look at the fault model here, our checkpoint theorem will tell you that you have to look at these faults also. Okay. But we are not doing that when we look at only this. Okay. So that is why it is important to have cell aware fault model. So this is becoming important in automotive, right? So Mentor and AMD, they did an experiment. They took 800,000 ICs meant for a 32 nanometer notebook processor. So when they use cell aware testing, which were aware of the faults inside the cells, they apparently some 699 parts failed. More than, see, I think this explains that, right? So 800,000 ICs were tested. So totally 699 fails, resulting in a 885 parts per million. Okay. So if you had 800k faults, if you scale it up to 1 million, the number of the ppm or dpm will be 1 million divided by 800k multiplied by 699. So I think that is what is 885. Okay. And they have done some Venn diagram here. So these are the cell aware tests which are stuck at 0, stuck at 1. These are cell aware tests which are like delay faults, transition delay faults, etc. And there were some which were common. So what they are saying is that if we had not done these cell aware tests, our DPM number would have not been correct. Okay, we would have supplied some bad parts to the customer. Okay, so we have discussed this already. So unfortunately, the problem with CAT is it increases the defect size. That means it increases the amount of testing that we have to do. Okay, they found that it improved 1% coverage increase, 5% improvement in coverage when compared to transition defect problem. Adaptive testing. Okay, what is adaptive testing? I think we mentioned it earlier also, right? So not all chips need the same amount of testing. Some population of chips need more testing and some need less. Okay, it depends on, for example, there is a strong belief that the chips which are at the periphery of the wafer, they are likely to fail, with reliability problems, etc. So an example is airport screening, right? See, in the airport screening, you may see that they always pick out a few people for more screening. They let other people go. Why? because the security guard has some feeling that this person is likely to be a problem. So they don't screen everybody the same way. Okay, so they use some information about the chip, right? They make measurements, and depending on the data in the measurements, they may pick a few people as outliers. So some of the chips will be picked up as an outlier. It could be because the chip lies in the periphery, right? And use the fact that defects tend to cluster. If you find that one chip is bad, then be very careful about all the peripheral neighbors. Track the number of bad chips in a neighborhood, and track if the parameters are outliers. So use some sort of an artificial intelligence for this. Okay, so this is an example of using AI. Okay, so if this is the X is the unit under question, that means that is a chip that we are. So this is a big wafer, right? N means the mean yield of 4 dies marked N. So you take the dies which are marked N, right, and take the yield of those 4. So the ones which are N, 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 N. Suppose 3 out of them pass and the 4th one failed, the yield is 3 by 4. Similarly, what is the mean yield of the 4 dice marked D? Okay. And T is the, so then they say that this is the local yield, and the dice that have small local yield but pass the wafer probing tests are reliability risks. So they have figured out a simple smart way of figuring out which chips are likely to fail. Okay, they are good, they seem to be okay now, but if you sell them to the customer, they may come back to us with problems. So that is what they are saying. There is also something called as part of average testing. So when chips are coming and they are being tested, so what they do is they when they measure the parameters, for each parameter there is something called as an LSL and an USL. This is the lower specification limit and this is the higher or the upper specification limit. Okay. Then if the chip has a value for the parameter which is either here or here, we consider it as an outlier. Okay. If it does not fall in this limit between LSL to USL, we say it is a. So how do you determine that? Okay, what they are saying is you can pick let us say something like the IQ. IQ means IDDQ. That is the current in the power supply, right? That is typically normally distributed. What I mean is, if I take a lot of chips and measure IDDQ, I will find that it has some distribution like this. Okay. So sample maybe about 30 parts from 6 different wafer lots, and maybe 5 zonally different dice. Okay, that means on the wafer pick 5 from very far off places, right? So you have collected 30, then obtain a robust mean. So whatever parameter you are measuring, some current or something like that, IQ, find the mean for these 30 parts and calculate a sigma by taking Q3 minus Q1 divided by 1.35, where Q3 and Q1 are quartiles. See, quartiles means see, you can divide the data like this, right? So Q1, Q2, Q3, Q4. So this is a minimum value, this is a maximum value, and we have divided into 4 quartiles. So these are Q1 and this is Q4. So they are referring that take the Q3 minus Q1 divided by 1.35 as the robust sigma. See, these are all statistical ideas, right? And then you can define the limit as sigma mu plus or minus 6 sigma. Okay. And that is how they are recommending. So this is just an example, right? So adaptivity, okay. So perform the wafer probing, and whatever fails in wafer probing, we throw it away, right? I mean, they failed early, and we may have used some predefined test for applying at the wafer level, and we can adapt it. If we feel that not many failures are occurring at the wafer level, there is no need to kill ourselves by doing too much testing at the wafer level. See, you may have seen this, right? See, suppose we go to a campus for interviews, right? See, let us say there are a panel of 3 people who have gone, right? And the first guy asks certain kinds of questions, and then whoever passes that, we ask the other person to ask these questions, and the third person. Okay, this guy asks easy questions, somewhat mid level, and this guy asks hard questions. That is how they have gone. See, this guy, if the easy question itself the guy doesn't answer, there is no point in him sending the student to these 2 places. So they reject. The idea is lot of people are there to be interviewed. So this guy is acting like a filter, and this guy is acting another level filter, and so on. Because these take a long time. These those who make it to this place, they may spend more time to in the interview, right? So they will have to adapt themselves. See, if they find that a lot of people are beginning to pass, right? So he has to adapt his questions. Suppose he asks the same question, then what can happen is these guys will figure out. They will talk to one another, and they'll start answering all the questions correctly. So he has to adapt. That's what we are also saying. So at every stage, you have to adapt. Okay. And there is a database that you have to keep in order to track which chips are passing which tests and so on. So for that, they are maintaining a database called as Rich Interactive Test Database. I want to go through this, right? This I have mentioned several times, so I don't want to mention this. Okay. This also we have seen this before. Okay. So let me conclude now, right? So I think I have mentioned to you that test is a career, right? And there are many exciting prospects. A lot of in India itself, there are companies that are coming up to offer test services, right? And you should develop a sense of pride. See, people look at design as a career, and everybody thinks that design is a very fancy thing to do, right? In the same way, test is no less, right? So that is what you have to understand. And industry is always looking for good design for test and test engineers. And you should also collaborate, right? Attend conferences when possible. And there are a lot of sources of information, I think I have mentioned. Right, I think I have mentioned to you books, and then there are websites. I have shown you where Vishwani's slides are available. You may not be able to buy the book, which is very expensive, but you can refer to the slides. In the same way, you will, if you search, you will find excellent sources of blogs, right? People may have recorded videos. Okay. See, for example, I think there is a very good source that you could follow called semiconductor engineering. So, if you follow latest developments, etc., they typically tend to carry blogs about these topics. So, there are many good such sources. So, follow them, and wish you all the best. Thank you.